Hello again. This is now not what I thought was going to be 60. I think it's 59. And it's going to be a little bit of a crazy tutorial. A lot of things are going to happen, hopefully in the right order and with the right results. But before going on, I want to point something out that's a little bit of a pet peeve of mine, and it's been bothering me for years. And that's this thing. You see, when you have classes that have virtual functions, which I now have, these classes are now able to be used with something called RTTI, Runtime Type Information. Where's it? See, Runtime Type Information, which is actually a compiler setting which you can turn on or off. I happen to have it on. Let's see now. I'm not sure where it is, but somewhere in here. Here, enable runtime type info. Okay, so now they've got this thing here called type ID, which returns a sort of a constant reference to one of these structs. Okay, and so you can use, for instance, you can find out the type information about the class. And one of the bits of information you can get is the name of the class in a human readable form. For instance, this base here, I could, if I wanted, print f %f the type name is that, and then I say type ID b do I need a reference? Name, something like that. Maybe we'll just compile. Oh, too much other output. Now I turn all the rest of it off. Turn everything into a semicolon. Okay, see? Type name is class base. Alright, don't forget about these dots. Now, okay, so isn't that wonderful? It told me the name of it was able to get the name of the type. Except, there's always a memory leak. See? It allocates some memory for this name pointer, but it never frees it. And according to the help here, you're not allowed to free it yourself. I'm going to say that. The name is actually where is it? Here. Type of name returns a null terminated string. The memory pointed to is cached and should never be directly deallocated. Well, they never deallocate it, and I'm not allowed to deallocate it. So then every time I use this thing, I have a memory leak. And eventually you get so many of these memory leaks that you start to ignore the memory leak report, or you just turn it off, or you go through great lengths, as I've done in previous projects, where I attempt to isolate the ones that belong to this type ID and modify the leak report. But I believe I've found the answer, and you don't even need runtime type info. There's a better answer to this, and it's in this virtual dance thing. And well, I don't know. Maybe I'll show you that later. But I found another way to do this. It doesn't require this and no more memory, so that's out of the way. Okay, now here is a class base B which has virtual functions. Okay, there are 4 of them. 1, 2, 3, and 4. And here I print them out and put these printouts back. And also I will compute the virtual table, virtual function table address. And I'll show you that too later. The class itself has one member data, a double, which I generate sort of randomly. So each new one will have a different value for that if I make more than one. And this global thing, the virtual function pointer to the address of the virtual function table, which should not change from one class instance to the next. If it does change, though, you'll see that change because where I compute it here, if it does change, I change the global variable. And it's defined here initially as no. But first, without looking at the code or anything at all, I just want to point something out. Okay, now here's B, and here's this VFPTR, okay, virtual function pointer. Alright. Now the value of this thing, whatever it is, happens to be that, okay? And they call this a VF table. Alright? Now, I'm going to point something out here. First, I want to put down the address of V. Okay? Now, I would like to see what the address of this thing is. Now, I don't know if I can do this by dragging, maybe. Yeah, I can't edit it, that's the problem. But I can still do it by manually. Address of B dot underscore B P BPTR, is it? BFPTR? Yes, that's what it's called. VFPTR. Address of B dot VFPTR. Okay. Now these are always the same for every object. The address where VFPTR is stored is the address where B is stored. So that's always true. So you can say, if you wanted to, that B is B points at, the address of B points at a virtual function table pointer. Okay, same address. If I made a second view, they will. It's true, B1 and B2 will have different addresses. But, as you'll see, okay, now what's the address of B1's virtual function table? PTR, VFPTR, something like that. That's the same as the address of B1. B2 dot underscore VFPTR. And that is the same value as B2. Now, this pointer here it appears to contain all the same entries. Same with this. Okay. Now what one should be curious about, the first thing one will be curious about, is what is actually there. And there's another address, 469D-A0. Okay? That's this address. Now we're going to this address and get rid of this modifier. Get rid of all. Four, 6, A0. Okay, now see here, there's another address, 40106E. Okay, now this here address, 6FDE9, what do you suppose 6FDE9 might be? Actually, am I reading this in the right direction? There should be 4 entries here. 1, 2, 9, 1, 2. It's reading this somewhere. 6E. Unless I typed it in wrong. Let's go back to that other address. 469D80. Okay. Trying to do things for me. 0040106E. 0, 0, 4, 0, 1, 0, 6, E. 6, F, D, E, 9. I've written it. Now how do I go back? I wish I could go back. What if this takes me back? No. Do it again. 469 DA 0 4 0 1 0 6 E, and then 6 FD. Oh, that is what I wrote down. 6 FD 9. Which is question mark. I would think that if it were something, it would. Okay, well. Oh, yeah, okay. Oh, sorry. 40106E is where we could have stopped. That's V func 0. That's what, okay, went too far. So, if you started at this here, 469 DA 0, okay, the first entry here is this one, V func 0. The next entry is 401055. That's V func 1, and so on. Okay, 4 entries. So this is the actual virtual function table. So this VF pointer points at a value, which is a pointer, again, to the table of pointers to functions. Okay? Now it turns out here that I've already computed this by a different method. But now what got me curious about this here is just the fact that address of any one of these B's, even though they're different, right? The address of B1 is equal to the address of B1 dot the PTR, whatever it was called. Okay, and they're all different. Each one has a different storage location for this particular member. This is typically on the stack. You saw. I'll run out to here again. Addresses B1 and B2. Those are on the stack. Okay, so these are actually members of the class as we were doing ourselves. And then starring that takes you to somewhere in the 46,000 area. Now, one of my curiosities actually was where if I malloc something, where does that end up? haven't tried this yet. I'm wondering if it's around the same area. So that is, yeah, okay, 6F. So it seems like the mallocs are around the 6,000s, and oh no, this is in the 4,000s. So that's not coming. These are not probably coming from malloc. They have their own secret malloc for these for this area. And now that other one, by the way, you'll notice that this one comes from another different area. These ones are always, oh no, it's not actually. So this is in the same area as these guys. Okay, well that's something of some interest. I thought this would be totally different. But this, yeah, this is 6s. Okay, so this is just a malloc, and these are just mallocs. Last time when I did this, it was 2,000 something. But maybe that, I don't know why it would have been different, but it was. Okay. Now I can always recognize stack. That always starts with 1, 2. These now 4,000 things I recognize as runtime type virtual data. Virtual data is there, and regular old malloc is in the 6,000. And nothing here is in the 6,000. These, when you dereference it again, it stays relatively not too far away. Probably these tables are created first, and then it just grew. I can't imagine it growing that big. Anyway, I'm rambling, aren't I? All right. Now the question is. The question that I wanted to answer was, is there any way I can just call one of these functions directly by, just casting? Because I know if I take this address, right, then I get a pointer to a pointer, which if I dereference that, I get another pointer, and that points to a table of functions. And I should be able to maybe cast one of those functions as a base colon, blah, 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 blah. And it wouldn't let me do it. No matter how hard I tried, it wouldn't allow me to convert it. So, not wanting to give up, I simply just coded it in assembler. And that is what I came up with. So suppose we have our base here. Well, here's one thing. First, I have a function now that will tell me how many virtual functions it has. Yeah, numVfunc. These are all template functions, and there's a reason for that. Printf class %s and %d virtual function. Now, here's my type name. Type name of E with no malloc problems. First, I'm going to show you that this works. Oh, yeah. Oh, that's true. Now, the reason why this is a template is because normally I don't know what type of thing I'm being passed into this function, but this will work. I could just type base here if I want. 7. Class base has 4 virtual functions. %s, I guess, is good enough. Now, you'll notice no memory leak. And actually, I put this in the debug trace here too, so that I can see it in the output window. So I didn't really need to print that out. Okay, now how does this work? Well, the type name thing is not that hard. I just use that special undecorate name, undecorate symbol name thing. I love this function. You see, I don't need runtime type info with this thing, because func decorated name is provided by the preprocessor. Okay, so it doesn't have to even be this type doesn't even have to be a polymorphic type. And then all I'm interested in finding out is the name of this function. Okay. And if I pass it any class, if I call this function with some class, right, and find out its name comes out. This will get called, so I can put F7 here. F10. Now, here is the name of the function. Blah blah blah. It returns a string, right? And the only place and the last place in the name of the function, undecorated, has within these angle brackets the name of the class that I've passed into this function. Okay. So now, in fact, if you look how this is being called, it's coming from num_vfuncs, where I've been passed a something, don't know, and I want to print out this info trace, so I call type name t, and that gives me this name for the function from which I can extract the name of the class. Okay, so that part's not too hard to understand. Right, it's taking the name of the class and extracting the substring using mit with our special string functions. Okay, now how am I finding out how many virtual functions there are? num_vfuncs. So now here's another thing. Let me just demonstrate it. Something. You may have noticed that before I said that I am no expert at templates, and there's a reason why I said that. Because templates themselves, you can do a lot of things with. But there's a category of things you can do with templates, which is like a whole other programming language all to itself, and I don't know very much about it. But I do know a few things, and one of them is to do with this, what they call template metaprogramming. Suppose it's clear that I can call this I did the non-defunct of B. Okay, I'm allowed to call that. But what if I called this function with an object that didn't have virtual functions? Now, one way to handle a situation like that is to look at the object, look at its address, and try to make sense of what's being pointed at and so on, right? Or check the size or something like that. Another way to do it is using this template metaprogramming, where the assertion that I've placed into the code, and you're going to see it go off, fires during compile. This won't compile. And when I press F4, it takes me to this assertion failed non-polymorphic type. Okay? Now that's a template assertion. But this is intentionally here, this type def, to draw my attention to the fact that I've made a mistake. I've passed a non-virtual thing into this function that expects something with virtual functions. Okay? Now how does that work? Well, that's using this object. See, the whole template stuff, the way it's organized is in C++ anyway. I don't think you can do this in any other language. Is in such a way that you can write code that the compiler, as it's doing its compiling, executes, and you can make the compiler execute code in a way that you desire. You could make the compiler compute pi, for instance, just by pressing Shift F8 or whatever your compile key is. But here's one of the ones that I learned. Is virtual. So is virtual is a template struct, okay, and inside this struct is another struct called _s that derives from t, whatever t is, okay, and it has a virtual function which is just given a dummy name, alright, and here's its empty constructor, okay. Now I've passed in a class B. Now this here is now making an instance of an _s using the B that I passed in, okay, and adding only a virtual function to it. Now if the B class already had virtual functions, its size would remain the same. That is, a class without virtual functions, or struct. Let me get rid of this for a second. Doesn't matter how much data is in it. You could have an infinite. If I print out don't do any of this. Size of A. Okay. That's going to come out to 4 in this case. Alright? 4. Now if I add a virtual function to this, that's going to add 4 bytes to the size of A, because it needs that virtual function pointer element, the secret hidden element. So now it's bigger, you see? If this was not virtual, the size of A would remain the same. See? So now going back to this thing here, here's this struct, that's like that capital A, which contains which derives from the object passed in and contains a virtual function that does nothing, just as I did there. Okay? Now I have this struct is virtual. I pass in some class. I build myself an underscore s using my passed in class and add a virtual function. Now this thing derives from t, which has been set to the passed in class. Now this thing is creating an enum, like a list of numbers with a single element called val, and val is equal to the value of size of b, size of underscore s of b being equal to size of b. So if these two things are equal, val is equal to 1. And if they're not equal, then val is equal to 0. Alright? I hope I haven't lost you yet. You're going to have to come back to this. Now, getting back to the template assertion, here I'm defining a type def of an integer array of size is virtual of t : val. Now it's illegal to declare any type of array of 0 size. So if is virtual t value is equal to 0, then this type def is a compiler error. So that means if this value is 0, which would only occur when these two things are different, right? When this is false, value would be 0. So that would mean the size of these structs are different, which means a virtual function table was added to the class that I passed in, meaning that that class is not virtual. Then I get a compiler error. So basically, this asserts at compile time that the passed in class type is virtual. I'm not allowed to compile this program with the wrong type of data being passed into this function. So I think I have to stop here. Just explaining that took so long. Yeah, okay. So I'll continue on with this with the next one. Alright, see you on the next one.